Alrighty, so today's discussion is about forces, and we're going to actually compute some stuff today. So this is forces part 2, and we're going to be using Newton's second law extensively today, but we're going to be building some uh, common sense ideas around it. Okay, so let's see. First things first. First things first. So let's draw some situations here and talk about what goes on with this. Let's presume that I have some sort of frictionless surface, and there's some sort of heavy, massive box sitting on it, and we're going to have two people pushing on either side. Uh, Person on the left pushing to the right with force F1, person on the right pushing to the left with force F2. And let's furthermore observe that there is no acceleration of this box. Now, no acceleration does not necessarily mean it's not moving. No acceleration just means that its motion is constant. So this box could be moving constantly at a constant velocity, but it's not speeding up or slowing down. Typically, in this situation, we are talking about something that is not moving at all. But we need to draw ourselves a free body diagram for this situation. So I'll go right below it and draw a free body diagram. And in the free body diagram, we need the arrows going away from the object, which is represented as a dot. Okay, so that's the free body diagram. I would get credit for that now. And so how do we solve this problem? Well, we need to calculate F net and set it equal to m times a. F net, well, F net is an algebraic sum, so we need to declare which direction is going to be positive. I'll go ahead and do that. Get it away from your dot. This is not part of a free body diagram, and I don't want the College Board seeing this near your dot. Maybe put it on the original drawing. But that means that we have a positive F1 and we are going to add to it a negative F2. And that's going to equal m times a, which of course is 0 because a was 0. So this immediately tells you that F1 minus F2 equals 0, or F1 equals F2. This is a proof of your common sense idea that if these two forces are being exerted in opposite directions on the object and there's no acceleration, that the F net must be 0. In other words, they must be equal to each other. So now that we've done this, you can conclude that. Let's do another little picture. Here's another situation. We have a ceiling beam and we have a rope hanging down from the ceiling beam, and we're going to put a big, heavy, massive object hanging from the rope. Let's draw a free body diagram for this object. And I'm even going to be so clever as to use red for the forces. But the object is a dot, and there are two forces on this dot. There is some weight pulling it downwards, and there is some tension pulling upwards. And if this thing is not moving, then the acceleration is 0. And we can conclude that the tension must be equal to the weight. And since weight is m times g, we now know that the tension equals m times g, and we can figure out the tension in this rope. That's the kind of thing you need to be able to do in order to analyze forces. Now, this process of drawing the free body diagram and making these deductions is training wheels. As you get better at this, the training wheels will come off of the bike. Okay, let's do something else. What about here's an interesting situation, kind of build this up. Here's a little wall, and there's a frictionless table. No, I don't care if it's a frictionless table, it's just a table. On the edge of the table, I'm going to put a pulley, that is to say a round thing, and I'm going to drape a rope attached to the wall, draped over the pulley, and then pulled down. And I want to know, what is the tension in this rope, assuming the acceleration equals 0. Well, the tension in the rope here at this point is exactly equal to the tension in the rope here at this point, because the tension in a rope is the same everywhere. That's something I wanted to say to you. Tension is same everywhere. That's what ropes do. They transmit the tension from one place to another. The pulley just has the function of bending the rope so it goes a different direction. So this situation is exactly the same as this situation with the rope hanging straight up, because if you cover up this spot right here, you see what we have is a mass hanging from a rope. So we can conclude from our previous example that the tension in the rope is exactly equal to m times g, the mass of the thing times g, or its weight, if you would like to do that. Okay, so far, so not so bad. But let's take one that is a classic example and that even PhD physicists sometimes have trouble with. Let's go ahead and let's have a pulley that is suspended from the ceiling. And now what we're going to do is we're going to have a rope, and there's going to be a mass hanging on this side and an identical mass hanging on this side. And we observe that the acceleration is equal to 0. What is the tension in the rope? Well, the tension in the rope, if you cover up everything and you just look at this mass, the tension in the rope is just m times g again. A lot of people think that the tension in the rope would be twice as much because there's two weights hanging, but it's not true. The rope doesn't care whether there's another mass on the left-hand side that holds the system to acceleration equals 0 or whether it's tied to a wall and there's some force exerted on the wall. It does not matter. So in this case, the tension is exactly equal to m times g, or the weight of one of these weights. These weights would have to be exactly the same mass in order for this to be true. We're going to have a situation later where one of them is heavier than the other, and then it's not possible for acceleration to be equal to 0, because when you compare the two, you'll see that the same tension that would hold one still is not the tension that would hold the other one still, so they can't both be still. All right, so I'm building this up. You can always draw a free body diagram and do the full-on math starting at Newton's second law, or you can use kind of what you've learned to set things equal to each other and set them equal to their recipe, the recipe for weight being m times g. All right, we can make this a little more difficult, and this is a lab I did in high school, and this is where the equilibrium forces get a little harder to figure out. This is going to be a metal ring, and we're going to tie to this metal ring, we're going to tie some ropes, and we're going to pull. This one's going to pull directly northward, and that's going to be F1. Okay, something just dinged at me.